Welcome back to our series on probability theory. I'm Mark Ledbetter, and this is lecture video 37, part B. We are doing part 2 of continuous bivariate distributions. So last time we introduced the joint range of x and y, and I emphasized the fact that this is extremely important for continuous bivariate distributions because we're using integration, and when you're integrating with double integrals, you have to be very careful about what you're integrating from and to in the correct direction. And then we introduced the joint PDF of x and y, talked about the properties of the PDF, the marginal distributions, and independence. So we're going to do an example today. We won't get to correlation regression in this video, but it will be in the next one due to time constraints. So let's get started. So I want to start by reviewing the example that we did last time, just the information. We're going to use this PDF, this joint PDF of x and y. So remember, it's x plus y when x and y are both between 0 and 1. And in this case, we had a rectangular joint range of x and y. Now we're going to ask a different question on this. So we're going to ask, what's the probability that x plus y is less than 1? So remember that f of x and y was equal to x plus y when x is between 0 and 1 and y is between 0 and 1, and it's 0 otherwise. Okay? So the first step has to be finding B. B is our subset of R in this case. And I'm going to start off with this inequality here, but I'm going to find the equal sign. Now, I'm going to find x plus y is equal to 1. I saw for y is equal to 1 minus x. So that is my dotted line here. X plus y equals 1 here. If I want to express this in terms of y, it's 1 minus x. If I want to express it in terms of x, it's going to be 1 minus y. And I will need both. This line on the bottom here is y is equal to 0, while this line here is x is equal to 0. Now, technically, I should have the x equals 0 and the y equals 0 dotted, but those are also my axes, so I am just simply leaving them as they are. Again, technically, this line where x plus y is equal to 1 should be dotted, all right? And but if you don't do that, I won't take off any points because it's not going to change any of the values. But I will mention that if someone else is reviewing your work, let's say a boss or a coworker, and you have, say, a solid line here when it's supposed to be dotted, and that may be all that they really remember. And so the one thing that they remember, they see that you've gotten wrong, and that can change their whole impression of your professionalism and their trust in your results. So while it may seem small, it could have a big effect. So I encourage you to do things precisely whenever possible. All right? So I need to find B, the joint, which is the joint range of x and y, which x and y in B, of course. So if I look at this and say, let me express x independently of y, okay? I'm not saying that x and y are independent because they are not. This is not a rectangular joint range here, so definitely they are dependent. However, I can express x by itself between 0 and 1, and then I have to express y dependent upon x. So if I'm looking at y here, I leave that. I'm going to blow up the picture so we can see it. If I'm looking in the direction of y, then I'm going to, let's use blue, I'm going to integrate straight up. I can't seem to draw a straight line, but I'm going to integrate from y equals 0 to y equals 1 minus x. So y is going to be between 0 and 1 minus x. And that is what I have put here for my range of y. Alternately, I can express y independently, and then I need to look at my picture and say, well, where does x, how do we how would we integrate x? What is the range of x in this case? So x is going to go between these two lines. Again, the line over here is x equals 0, and this dotted line in terms of x is 1 minus y. And so that is how I express x in this case. Please remember that the probability that x plus y is less than 1 is the same as the probability that x and y are in B. These are equivalent. Okay? This is a set function, and this is just a probability function using the random variables, right? So the second step is we're going to choose to find the probability of this, and we have to choose which variable is going to be dependent and which will be expressed independently. All right, so first I'm going to do both. I'm going to express x independently of y, and then y is going to be expressed dependent on x. So that is this first case here. And so when I set up this double integral across the space of B, okay, with f of xy dy dx, I have to integrate y first because y is expressed in terms of x, 0 to 1 minus x, and then x is just 0 to 1. So I have to put dy first, and I'm going to integrate that inner integral first. You are welcome to write it separately, but you don't have to. I used to long ago. Now I can just use brackets and do it inside the integral, whichever is easier for you. Just get the right answer is the key, right? All right, so if I integrate x plus y with respect to y, I get xy plus 1/2 y squared. And again, this is inside before I integrate with respect to x. So I have to plug in for 1 minus x and for 0. Well, notice that and you'll also notice that I wrote y equals 0, so I plug into the right variable. There's a y in both terms. If I plug in 0, both terms are 0, so I'm left with 1 minus x, plugging that in for y. So I have x times 1 minus x plus 1/2 1 minus x squared, and that's here, and then still dx. I simplify this, expand it out, and then cancel the terms, so I end up with x minus x, and I end up with 1/2 x squared and negative x squared, and then just the 1/2 by itself. So I have 1/2 minus 1/2 x squared dx. I integrate that. I get 1/2 x minus, and remember I raise this 1 to 3 and divide by that. So I have a third and then a half. So a third times a half is a sixth. And so I have this expression. When x is 0, the whole thing is 0. So when x is 1, I have 1/2 minus a sixth, and a half minus a sixth. If I put it all as terms of common denominator, I get 2/6 or 1/3. Either of those is fine. Now, so that was letting x be expressed independently of y. Now I'm going to express y independently of x. So y will be the second integral from 0 to 1, and x will be the first inner integral, and it's going from 0 to 1 minus y, x plus y dx. So I'm integrating that with respect to x. I get 1/2 x squared plus xy. Again, and I forgot my dx. Need that. Equals. So I need to evaluate that before I do my next integration. So I plug in for 0. Both have a x, so that's 0. So I simply plug in 1 minus y for x. So 1/2 1 minus y squared plus 1 minus y times y. And simplify that, and I get the integral. Oh yeah, and this was not dx up here. This was dy. Okay, so this was dy. And so I simplify here, and I have a negative y and a positive y. I have a 1/2, and then I have a 1/2 y squared minus y squared. So I end up with 1/2 minus 1/2 y squared. Basically the same here up in the x's, except switching x for y. I take the integral of that with respect to y, 1/2 y minus 1/6 y cubed, plug in 0 and 1, end up with, again, 1/3. I'd better end up with the same value both times. All right, So I want to mention, and I will pick up here next time, that the correlation and regression, the properties of covariance and correlation for the discrete case are the same as they are for the continuous case. The only difference is that we switch summations to integration. Okay, so that's all the time we have for this video, so I will pick up here next time and do that other example. So please don't forget to scan and upload your lecture notes before midnight, the date listed in the course calendar. If you have questions, come to virtual office hours. If you can't do that, then by all means, please email me. But when you email me, I need you to send me two things, a picture of your work and a picture of the problem, and I will be able to quickly see what you're thinking and know the problem and get back to you fast. So I hope you'll take care of yourself, and we hope to see you next time.